So good afternoon. I'm going to talk about neutrinos in the very low relating scenarios. And at the end of this talk, this talk is divided in two parts. So the first one, it's about updated constraints on very low heating scenario. And it's basically an update of some analysis that were done in the past about this kind of models. And in the very last part of this talk, I'm going to discuss some generalization that was anticipated in the talk by Sergio this morning. So why reheating? Of course, if we believe the inflation paradigm, we need a reheating because we have to match at a certain point the Friedman-Lemaitre-Robertson-Walker universe with his radiation-dominated epoch at the beginning, you know. And in the standard picture of inflation, it is driven by a scalar field that dominates the energy density that's slow roll into about on this potential that at the end of its life, let's say, start oscillating around the minimum and decaying in the standard model particle. So this is what we call reheating. And in particular, from the equation of motion, no. Okay, it is possible to define a reheating temperature comparing the Hubble ratio with the decay ratio of this scalar particle. And we see that the reheating temperature is just a proxy to indicate the decay ratio of this scalar particle. So why the interesting in low reheating? So in the past few years, actually, there were not so many papers studying constraints from cosmology about these models, but there were some of them. These are four of the most in the main ones, and all of them had a high number of citation. And the interesting fact is that this started to increase from 2015. So apparently these numbers start to become important for people from the book, probably even before, but in the past year, the interesting started to increase. Some remarks about our model. So low heating in our picture is a scenario in which the inflaton, or the scalar particle that decays into the standard model because of freedom, is coupled to everything apart from neutrinos. Neutrinos are populated by weak interactions with leptons, and also something about terminology. We define low reheating when this occurs at temperature below 20 MeV. And okay, as was pointed out by Stefano this morning, oscillations start to be affected at below 8 MeV. So we have also to take into account this effect. The formalism that we used to study this kind of model, as was already explained this morning, is the one of density matrix equation. I don't want to talk again about this. Essentially, we are following the distribution function of neutrino, the density matrix actually, given in terms of flavor distribution function, and we are evolving it into the early universe, considering vacuum oscillation, so due to the mass splitting, matter effects, and collision integrals. We solved this equation into a low rating scenario with the fortepiano code, actually with a modified version, and we obtained this kind of plots. So on the left, we have the time of evolution of the ineffective parameter in terms of the time, of course, in terms of reading temperature. And we can see that for very low reading temperature, like 3 MeV, we can obtain ineffective values that are very different from 3, actually almost 0 in the lowest case. And on the left, instead, we have the final distribution function of neutrino per each flavor at the end of the run of the code, but this started just to free stream after the neutrino decoupling, so it's gonna be constant in the co-moving volume, and we can see that this is have a lot of non-thermal distortions when the reading temperature again goes to very low values. At the end, it's possible to build this kind of curve that is a one-to-one relation between the reading temperature and the final and effective. And from this, it's possible to obtain a very rough bound on the reading temperature, just comparing this with the sensitivity of cosmological experiment. In the origin, okay, not the original paper, in the last paper, it was also by Sergio and collaborators, the most stringent bound found was around 4 MeV. And by direct comparison, you obtain just a 3.5, let's say. Here we are updating with the new datasets. In particular, we are using Planck 2018, and instead of 15, we are adding the BAO. And with this rough comparison, we can see that we are going to increase by half of a MeV. It is interesting to notice also that with futuristic experiment, actually not so futuristic, given that Simon's observatory is going to take data very soon, we can bound this to, I won't say a very high value, but we will almost be able to rule out this kind of model. But I'm going to talk about this in a while. So the first protest we have for these models of flow rating is the Big Bang nucleosynthesis. The distribution of neutrinos contributes through the total energy density to the Hubble expansion rate and to the continuity equation. And this has been taken into account thanks to a modified version of the Parthenope code, computing the abundances of the liked elements. Also, the distribution function of electron neutrinos as a function of momentum, of course, is appear in the weak rates that are used to compute the neutron-proton chemical equilibrium. And so it is these observable, I mean, these quantities are important for the abundances of like elements. And here in particular, the blue line is in this plot is the ratio between the deuterium and hydrogen. And in this one instead, we have the helium yield. Again, these are from the last paper, is not the updated analysis. And in that case, okay, this plot is quite new, but the bound is from the past paper. And it's possible to build a sort of chi-square and to take the 2 sigma bound. And we see that BBN is spoiled out if T reheating is, okay, it's the opposite here. It's less than for MEV. No, sorry. It has to be greater than for MEV. I'm sorry. So then we started to look at the cosmic microwave background. Also in this case, we have a sensitivity to the neutrino distribution function, but actually just to its final form, because at the redshift of interest for the CMB, it is just that shape that is important because of the redshift. And also, CMB anisotropes are sensitive to the primordial helium abundance, of course. That is the so-called Big Bang BBN consistency. We are taking into account this effect in a modified version of class and the Monty Python sampler. This is just a sketch of what happens, for example, to the TT power spectrum of CMB in some lower heating scenario. We have a modification of the peaks, especially in the high GEL region. Well, we started running with the modified version of Monty Python. At the beginning, we decided to do the analysis with 2 strategies. So sampling on T reheating, as in the past works, not only the one of my collaborators, but all the previous one. And then sampling also on an effective. This is because we noticed that sampling on T reheating, we were not sampling in a uniform way all the region of the low rating models, because effectively these kind of constraints come from a constraint on an effective, no? But if you are sampling directly on T rating, your model are pointing to the low rating region, because of course rating has to be at high temperature. But in this way, you are not exploring the part at low and effective. And to do this, we decided to sample also in this different way. And we can observe that indeed the contours are quite different. In the case of an effective sampling, we have larger contours that probably are due to this extending sampling on the low heating temperature region. Okay, the bounds on T reheating are this one on this table, and let me comment about this. This is fully compatible with what was found in the previous work. The point is that Planck 2018 is not adding a lot of information with respect to the 2015. And since we are using a modified version of the code for the piano that points to systematically larger value of an effective compared to the previous work, because of the new physics that has been added, we expected somehow the bound to be the previous one. Something interesting happens if we look to the ineffective sampling because this bound is a bit relaxed. Okay, here there is a Bayesian statistic problem because of course in the space of posterior of T reheating we find a peak because sampling on T reheating we found this. Then one has to translate the posterior in terms of T reheating when sampling on ineffective. And due to the change of coordinates, let's say, a peaks appear due to the Jacobian of the change of coordinate. And so this is a sort of an artifact. Indeed, the bound was written just taking the bound on an effective and translating it into a bound for T reheating and not integrating the posterior. The analysis was carried out also for the neutrino masses, again sampling both on T reheating and then effective, and this was done to check the robustness of the limits on neutrino masses, because this is a very strange scenario, no? Very different from the lambda CDM. And what is interesting is that in the past paper with Planck 2015 data, it was found a dependence on the limit on neutrino masses on the prior of the reheating. Let's say pointing the code, sampling on a very low reheating region, let's say at the beginning, the reheating less than 15 MeV, then less than 10, less than 5, less than 4, and this way, you find something that is sort of a relaxation on the limit of the sum of neutrino masses. But here, this is not observed. Okay, there is not the plot here because the chain was not well converged at this point, but it was a bit quite clear that it is not observed. And we think that actually we checked that this is due to the addition of the BAO to the datasets that is killing essentially the region of the parameter space that was providing this behavior. To assess our strategy of sampling, we computed the Kullback-Leibler divergence. This is a tool on Bayesian statistics that's a sort of notion of distance in the distribution, the probability distribution space. We computed the distance between each prior and the corresponding posterior, and it is possible to observe that we have a preference. Well, preference, it means that this one is more informative. There is not a preference for the model, of course. This strategy of sampling is more informative than the reheating one. With informative, I mean that we are drawing more information from data than from the prior. So this seems to be a better prior than the uniform one on T reheating, even if it is not well intuitive in my opinion. Let me add something on the scenario with the sterile neutrino. So why these kind of scenarios are interesting? One can generalize, of course, the picture of neutrino, adding a new sterile states, as we have already said this morning out of time. So the parameter space is enlarged by new mass splitting and triangles. But for the analysis, we are focusing just on a benchmark model with one mass splitting, the mass splitting at just one angle different from 0. And the point of this one, this scenario, is that thanks to the sterile, thanks to the low reheating, we can obtain some values for an effective, even with the sterile, that are way smaller than 4. For example, with the scenario pointed out by short baseline oscillation, you expect an effective of 4. But taking a reading temperature of about 4.5 MeV, we have this black dotted line that provide an effective almost equal to 3. So this model are sort of a way to reconcile the cosmological observation with the short baseline best fit preference for the addition of sterile neutrino. And it's interesting probably to study this kind of scenario in the early universe to understand what is going on. But what I was saying in the beginning is that in a few years we will be able probably to rule out this kind of scenario, so the problem will arise again. I just leave with my conclusion, and thanks you for the attention.
Thank you. Questions or comments?
When you look at sterile neutrinos at low reheating, sorry, were you?
Okay.
Oh, sorry. So what? Starting at 4.5 MeV, for instance, the Fortepiano code with just active neutrinos and no sterile, or
No, with the sterile.
but how are they produced with, like, reheating? It only produces active neutrinos or also sterile?
The sterile are populated. Okay, you observe it from here by oscillation with the active neutrinos. Yes. Okay, where is Stefano? Okay, I think.
So the actual implementation is that the fluid of plasma, the electrons, photons, and neutrinos is at very low temperatures, and there is only the inflaton. Then the inflaton decays at a temperature T RH, and then the active neutrinos are produced through oscillations and mixed through the sterile. So sorry, the active neutrinos are produced in interaction with the electrons, and then the sterile through oscillations. But they basically from a negligible energy density, and they appear later. Yes. But to answer, Fortepiano starts at much higher temperature than just 5.
Yeah. No, the only modification is the reheating temperature. Okay, the addition of the sterile, but then.
Is there a motivation for this lower reheating temperature, or is just a fit parameter?
Well, it's just putting. I think there are some old papers pointing out some scenario in which you have a rating. Okay, let me add something. I want to point out this. Rating is not always the rating of inflation, okay? We're bounding the last decay of a water particle to the standard model degrees of freedom. So you can have the rating of inflation, then populating something else, a dark set or whatever, that then decays to the standard model particles. And in that case, you're bounding that reheating, okay? So there are scenarios in which this happens. They are well motivated nowadays, but who knows? The point is that in this way, you can put a bound on this value, the reheating temperature, that is, I mean, the only assumption are these ones. No, you don't need assumption of about the particles, about whatever. You have a, okay, okay. These are the only assumption. So it's quite general. It's just a bound on the number.
So let me just add a comment, because I mean that the scenario of 3+1 is a neutrino low reheating temperature.
Okay.
Was, considering a paper I wrote 20 years ago with Graciela Gelmini and Silvia Pasco.
Sorry, say it louder.
So we wrote a paper on that 20 years ago with Graciela Gelmini and Silvia Pascoli
Okay.
on 3+1 with low reheating temperature. So yes.
Okay. Good to know.
Actually,
there is now, and the motivation is that we don't know anything of what happened before. So we don't know what is the reheating temperature left. So it's just, so the idea behind that is basically that it's just because you can make a very large mixing angles available because you suppress the production. Well, this paper I'm talking about is 2004.
And concerning the collisional integral, you implemented the full one?
It's the same. I mean, what do you mean with full one? Okay, Stefano, I think that there is no approximation on the diagonal terms, but on the off diagonal, yes. Dumping, okay.
Since I remember that there was years ago, in which they tries to do of course,
A complete way.
9-dimension integral, so they reduce it to 2, but they tried to solve these conditional integrals in the reading scenario, and they encounter a lot of problems. For this reason, I asked.
Numerical problems, you mean? Numerical ones? Oh.
So we actually checked that with the full collision terms, it's possible to solve the integrals and it works. It's just inconvenient numerically because the damping approximation work very well. And so we do the calculation with damping.
I have to check, but I remember this paper of Japanese guy. that-
Okay, we didn't
Hmm?
encounter any difficulties.
Okay, okay,
They
but
work.
of course, I mean,
So if there is no question, probably we can move to the last talk. Okay, so let's take Nicola before.